All right, so with gas stoichiometry examples, we're going to need to remember a conversion factor that we learned earlier in the year. Something about what is referred to as standard molar volume, or in other words, the volume that 1 mole of any gas occupies at standard temperature and pressure. Does anybody remember this little conversion factor right here? Let's see. 1 mole of any gas at STP equals 22.4 liters. Does that number sound familiar? Yes? Okay, that's what we call standard molar volume. 1 mole of any gas at standard temperature and pressure occupies a volume of 22.4 liters. That particular equivalent statement can be put in the form of a conversion factor. A conversion factor is just taking an equivalent statement and putting it in the form of a fraction. We can put 1 mole over 22.4 liters, or we can put 22.4 liters over 1 mole, depending on how we need to set up the problem, what units we start with, and what units we're trying to end with, okay? But that is going to be the equivalent statement that we're going to need to use in these problems, okay? In this particular problem, it says, consider the reaction between potassium metal and water. So we're going to need to start by writing out a balanced chemical equation. Remember, rule number 1 of stoichiometry is always start with a balanced chemical equation. So potassium plus water, and it tells us that when potassium and water react, that it produces potassium hydroxide, whose formula is KOH, and hydrogen gas, whose formula is H2. So there's our skeleton equation. K plus H2O yields KOH plus H2. Is that equation as is it balanced? No, that equation is not balanced. If we look at it, we've got 1 potassium on the left and 1 potassium on the right. We've got 2 hydrogens on the left, but how many hydrogens do we have on the right? 3. We've got 1 plus 2, which is 3. We've got 1 oxygen on the left and 1 oxygen on the right. So our hydrogen is not balanced, so we've got to work on that. Remember that this is a scenario where we've got an even number of hydrogens on one side. We've got 2 on the left, and an odd number of hydrogens on the right side. We've got 3 on the right. Which one of these substances, the KOH or the H2, is making the number of hydrogens on the right be an odd number? Is it the KOH or is it the H2? Which one makes that an odd number? The KOH. So we go to the thing that's making the hydrogen be odd, which in this particular case is the KOH, and in front of that we're going to put a 2. So that now the number of hydrogens on that side is going to be even. We now have a total of, here we've got 2 hydrogens in KOH and another 2 hydrogens in H2. So what is the total number of hydrogens on the right side now? 2 times 2, or 2 plus 2, that's 4. Okay? So how can we get 4 hydrogens on the left? Because right now we've only got 2 hydrogens on the left. How can we get 4? Put a 2 coefficient, good, in front of the water. Okay? So now we've got 4 hydrogens, but now our potassium and our oxygen are not balanced. How many potassiums do we have on the right? 2. How many potassiums do we have on the left? Only 1. So how can I get 2 potassiums on the left? Put a coefficient of 2 right there in front of the potassium. Okay? And we've still got to work on oxygen. All right? We've got 2 oxygens here in the water, and we've got 2 oxygens here in the KOH. So our equation is now balanced. So we've got coefficients of 2, 2, 2, and in front of the hydrogen, we've got a 1. Remember that when there is no coefficient in front of the substance, that the coefficient is 1. All right, so we've got our balanced chemical equation. After we get a balanced chemical equation, directly underneath that, we're going to write what information we're given and what information we're solving for. So in our problem, it says that we've got 0.500 moles of potassium. So over here under potassium, we're going to write 0.500 moles. And then it says how many liters of hydrogen gas will be produced. So over here under the hydrogen, The question mark is how many liters. So we're trying to go from moles of one substance over here to liters of another substance. But remember, if I'm going to convert from one substance to another, what unit do I have to go through? What is that unit that when you go from one thing to another, you've got to be in? It's got to be in moles. So I need to first convert moles of potassium into moles of hydrogen. How do we convert from moles of one substance to moles of another substance? How do I do that? How do I go moles of one thing to moles of another? Anybody? How do I go from moles of one thing to moles of another?
You cancel it out and then put that in.
Okay, I need to cancel out units, but where am I going to get my mole ratios from?
Oh,
Not the periodic table.
coefficients.
The coefficients. You got it, Lydia. Okay, so we need our coefficients to tell us the mole-to-mole ratio between the potassium and the hydrogen. So from our equation, how many moles of potassium do we see in that balanced chemical equation? 2. So we're going to write 2 moles of potassium on the bottom. That's a K right there. Okay, 2 moles of potassium on the bottom. And then we need this coefficient over here in front of the hydrogen. What is that coefficient in front of the hydrogen? What is it? 1. So 1 mole of hydrogen goes on the top. So now moles of potassium cancels out. And we're left with moles of hydrogen. Now, our last step, we need to convert moles of hydrogen into volume, liters. So to go from moles into volume of the same substance, that's where this conversion factor, 1 mole of any gas at STP equals 22.4 liters, is going to get used. I'm going to take that equivalent statement, 1 mole equals 22.4 liters. I'm going to take that equivalent statement and put it in the form of a fraction. Now, do I want my 1 mole of gas to go on the top or the bottom of this fraction right here? The bottom. Why do I want it on the bottom, Savannah? So I can cross out my units. So my 1 mole of hydrogen is going to go on the bottom. What am I going to put on the top then? Say it louder. 22.4 liters is going to go on the top. 22.4 liters of hydrogen. And so now my moles of hydrogen cancels out. So when I go to enter this into my calculator, what am I going to enter? I'm going to start with 0.500, and then what am I going to do? Times by what? 22.4, and times 1, if you want to throw the 1 in there. Okay? And then what? After I times by 22.4, what am I going to do then? I think I heard divide by 2. Divide by 2. You got it. Okay? The things that go across the top right here, that's what we multiply. And then the things that are in the bottom right here, that's what we divide by. Okay? So it's going to be 0.500 times 22.4 divided by 2. How many significant figures did we have in the number 0.500 over here? 3 significant figures. That is correct. Start with the first non-zero digit and then count everything after it. So that's 1, 2, 3 significant figures. What's that? Because right here in this denominator we see a 2. Does that make sense? Okay. So 0.500 times 22.4 divided by 2. And then we need to round our final answer to 3 significant figures. Okay? So when I type that into my calculator, 0.500 times 22.4 divided by 2, my calculator gives me 5.6. Is that 3 significant figures? 5.6, what is that? That's only how many significant figures? 2. That's 2 significant figures. How can I make it 3? Add a 0. So it's going to be 5.60. And then we don't want to leave that naked. That's going to be liters of hydrogen. So our final answer there is 5.60 liters of hydrogen. And we're done. Okay?